Okay, so this is where we were last time. Okay, now what I want to do is I want to carry this a little bit further. Okay, so let's go further. All right, so I'm going to add another joint. Okay, so this time I'm going to add another joint. Essentially, I want to go back to the wrist mechanism. Okay, so let's draw that wrist again. So here's the ceiling. Okay. So remember this. Right? So we had three revolute joint axes. Okay, we have rotations around this axis, that axis, and that axis. Okay, the angles theta 1, theta 2, theta 3. Okay, and we had a gripper right over here, and a fixed frame, or a moving frame. Let's use another color here. Okay, so that was my end effector frame, or the moving frame for this problem. And we can have a fixed frame somewhere. As shown. Okay. Okay, so it's really the manipulator I drew before with one more axis added, okay, because we're only looking at orientation. Okay. So the question I want to ask here is, well, we know this question, first of all. Given theta 1, theta 2, and theta 3, what is the orientation of this end effector frame? We know how to do that. Okay. Now, the question I want to ask this time is, given theta 1 dot, theta 2 dot, theta 3 dot, okay, given rotations, okay, angular velocities, okay, joint velocities, what is the angular velocity of this frame? Okay, so let's answer that question. Okay, so before we do that, we have to write the forward kinematics. So I'm going to do that quickly now. So the rotation r of the moving frame, and let's remind ourselves this is the forward kinematics. Forward kinematics, okay, and this is the orientation only. Okay, we don't need to worry about the position because the position is always fixed. Okay. All right, so r is, as you know, e to the omega 1, theta 1, e to the omega 2, theta 2, e to the omega 3, theta 3. Okay, we know it can be written that way. Okay, what's omega 1? That's the z-axis, so it's just 0, 0, 1, omega 2, the y-axis, 0, 1, 0. Finally, omega 3 is the x-axis, so it's 1, 0, 0. Okay, so put all these in there. Okay, that gives us the forward kinematics. Okay, that's not the real question I want to ask. The real question I want to ask is, what is the angular velocity given joint rates theta 1 dot, theta 2 dot, theta 3 dot? Okay, so for that, I need to calculate r dot r transpose. Okay, so I need to find, I want omega s. I want that. Okay, so this is going to be r dot times r transpose. Okay, we did this calculation before, okay, and it's essentially the same, very little changes. So we have omega 1, theta 1 dot, plus e to the omega 1, theta 1, omega 2, e to the minus omega 1, theta 2 dot. Okay, and then we have one more term because we added one more joint at the end. Okay, this term is going to be e to the omega 1, theta 1. Oops, let me write that again. Okay, now there's a e to the omega 2, theta 2. And then finally we have an omega 3 in screw symmetric form in the middle. And then on this side we have e to the minus omega 2, theta 2, e to the minus omega 1, theta 1. All this multiplied by theta 3 dot. Okay, so this is what we get. So it looks a bit messy this way. It gets a little bit simpler if we just write it in vector form. Okay, so let's use that trick again. Bring the rotation inside. Okay, and then we get omega s is omega 1, theta 1 dot, plus, same thing as before, e to the omega 1, theta 1 times omega 2, theta 2 dot. And then the third term, okay, just treat this as one rotation matrix. Okay, use the same trick. We get plus e to the omega 1, theta 1, e to the omega 2, theta 2 times vector omega 3 times theta 3 dot. Okay, all right, so we can answer the question now, right? So given joint rates, theta 1 dot, theta 2 dot, theta 3 dot, what is the angular velocity? Well, put it in this formula, and you get omega s. Okay. All right. Let's work out the details. Okay. Normally I don't do this, but no, in this case, let's just go through it. Okay. Okay. Omega 1 is z-axis. 0, 0, 1. Theta 1 dot. Okay. What's this? This is the rotation around the z-axis. So let me just write it C1 for cosine theta 1 minus S1, S1, C1, 0, 0, 0, 0, 1 times omega 2, which is 0, 1, 0. Okay, times theta 2 dot. Okay, one more term. Okay, third term. Rotation around z multiplied by rotation around y. Okay. So plus rotation around z, C1 minus S1, S1, C1, 0, 0, 0, 0, 1. Okay, times rotation around the y-axis by angle theta 2. So this is C2, 0, minus S2, minus goes down here now, 0, 1, 0, S2, 0, C2, okay, multiplied by omega 3, which is the x-axis, 1, 0, 0, times theta 3 dot. Okay. All right, let's add it up. And I'm going to write it this way. Looks like it's a linear combination, okay, involving theta 1 dot, theta 2 dot, theta 3 dot. Okay, so let's see, what goes in the first column? 0, 0, 1. Okay, theta 2 dot. Let's see, this times 0, 1, 0. That's just the second column here. So we get minus S1 plus C1, 0. Okay, oh, this one looks like a headache. Not too bad, though. 1, 0, 0 times this, just the first column. Okay, this times the first column. So let's see, there's C1, C2, plus 0, plus 0. So this is C1, C2. Okay, S1, C2, plus 0, plus 0. So it's S1, C2. And then last one, 0 plus 0, minus S2. Okay, not too bad. So I'm hoping I didn't make any mistakes here. So we're not done yet. All right, so this is pretty good. I'm going to give this matrix a name. I'm going to call it J sub S. This is theta dot. Okay? So I have here a formula for omega S, okay, which is the angular velocity, okay, of the end effector frame. Okay? It's some matrix J, function of theta, times theta dot, the joint rate vector. Okay? All right, so if anybody ever asks me what is the end effector angular velocity given that the input joint rates are theta dot, okay, I say, okay, easy. Give it to me. All right? I have my J sub S, so I just multiply that by theta dot, and I'll say, well, here's your angular velocity. Okay? All right, so suppose somebody says, okay, I want to generate this angular velocity. Okay? So here's the end effector frame. I want this end effector to spin around this vector by some rate. In other words, I want the end effector to have this angular velocity. And they ask me, can it be done? Can it be done? Okay? So, given omega s, given some desired omega s, okay? Does there exist theta dot that generates that desired omega s, okay? Such that, another way to say that, okay, such that 1 is true. Okay? Okay, so this is asking, can this wrist mechanism generate any arbitrary angular velocity? Okay. How do we answer this question? How do we answer this question? Okay. So given some vector omega s, does there exist some vector theta dot such that this is true? Okay. Given some vector b, does there exist some vector x such that a times x equals b? All right, so this is your, the standard question. right? Ax equals b, right? And nice thing about this, it's exactly the Ax equals. No tricks here. Okay, it's not like the forced closure thing. Okay, where you have to worry about the solution has to be non-negative. Okay, here it's just standard Ax equals b. Okay, so what's the answer? Or how do we answer that question? Well, in order for a solution to exist, Js has to be non-singular. Okay? Oops. So J sub s must be non-singular. Okay? So how do we determine if a matrix is non-singular? Well, one way to do it, in this case it's 3 by 3. Simple enough. Check the determinant. Okay, check the determinant. Let's do that. Determinant of this J. Okay, remember how to take determinants of 3 by 3 matrices? Let's just use this as the pivot. So it's this times this minus that times that. Okay, so it's just, all right, where is it? So it's so it's minus S1 squared C2 minus C1 squared C2. Okay? Which if I write it out, it's minus cosine theta 2 times sine square theta 1 plus cosine square theta 1, right? Which any self-respecting ninth grader, okay, knows is 1. Okay, minus cosine theta 2. Okay, so when does this equal 0? Okay, so if we force it to equal 0, okay, this tells us when it becomes singular. So it becomes singular when theta 2 is equal to what? Pi over 2, or 3 pi over 2. Okay. All right, so when theta 2 is pi over 2 or 3 pi over 2, we have a problem here. Okay. J becomes singular, so that means the end effector frame cannot generate arbitrary angular velocities at this posture. Okay, so let me draw that wrist again. Okay, so we had this time we're in this configuration. Okay, so this axis and this axis all line up. Okay, joint axis 1 and joint axis 3 are collinear. Joint axes 1 and 3, okay, line up. Okay, so in this configuration, we cannot generate an angular velocity in a certain direction. Okay, what direction is that? Well, okay, tells us right here. Okay, put in theta 2 equals 0. Okay, you'll see what happens. Now, this should also, okay, when we first studied rotation matrices, right? We use this as an example. Okay, when we're discussing Euler angles. Right, alpha, beta, gamma. We said when beta equals 90 degrees, right, these strange things happen, right? When beta equals 90 degrees, we get an infinite number of solutions, a one-parameter family of solutions, right? Everywhere else it's normal, behaves normally. But when this equals 90 degrees, just it gets messy. Okay? This is called a singularity. Okay, it's a wrist singularity. Okay. So in this, let's see. So we have some frame here. Let's see. So it's, I guess, yeah, something like that. Okay. So in this configuration, okay, it's impossible to generate angular velocities, okay, this way. Okay. In other words, you can't rotate this around this axis. Okay. If you don't believe me, try it. Okay, I dare you. If you can do it, I'll give you everything I own, which isn't much, but okay. It's a singularity. Okay. All right, so we're going to talk more about singularities in the next lecture. Okay, but okay, so this is a roadmap of where we want to go. Okay, we now understand angular velocities. Okay, from that, we figured out the relationship between joint velocities and the end effector angular velocities. Okay, and we found out that it depends on this matrix J sub S. Okay, and the matrix J sub S gives us a lot of information. Okay, things like singularities, for example. Okay, all right. So that's the program. Next step.